समुद्रवसने देवी पर्वतस्तनमण्डले विष्णुपत्न्यै नमस्तुभ्यं पादस्पर्शं क्षमस्व मे. Those who dare to fly don't care to leave their footprints behind. Welcome to FVS. Very good morning, everybody.
Morning, sir.
Morning. Are you able to see my slide?
Yes, sir.
Okay.
Yes.
Excellent.
Yes, sir.
So let's go ahead with the 15th class of flight vehicle structures, where we are talking about assumptions in the last few days, and we will continue with that. As I said, this is the most critical portion of this course, because it's important for us to understand the implications of the assumptions that we are making, and when not to make some of them, and to look at better models, some of which we will not look at in this particular course, but at least you should be aware that they are available when needed, because we cannot just go with a simplistic model. When the situation demands, we have to move up the gear in order to look at more advanced models which are applicable in such situations. And flight vehicle structures present us many such situations. So, which is why I am repeatedly emphasizing on these facts, that we have to check, one, whether the assumptions are necessary, and the second, whether they are relevant. So the relevance is what gives the particular situation, we say whether it is applicable for that situation or not. But the necessity is actually in the sense that we should not go with some assumption which may not even be necessary for the derivation, and we'll see an example of that probably in today's class or in the next class. So again, coming back to the font color that I have used, as I mentioned already in the previous classes, the green font is used to say that these are reasonably good assumptions, in other words, both necessary and relevant. Necessary to simplify the whole process. Without them, things will look much more complicated. And relevant because most of the composite structures and metallic structures within the yield limit are those which will agree to these assumptions, and therefore the mathematical derivations that we do and apply to these structures, whether for analysis or design, would be good enough. So the first six were of that kind, except for the material linearity. To some extent, we have to see if it goes to the nonlinear limit to basically bring in that aspect. But for that, for most situations in flight vehicle structures, these six are valid assumptions. So in today's class, we will get on to those which are a little more dicey, and which have replacements. Unfortunately, many people, both in the industry as well as in academia, continue to use some of these assumptions beyond the sixth one that we are going to talk about today. But I'll just indicate what are the issues with these assumptions, and also what are the alternatives which are available, without going into too much of details of the mathematical modeling of those alternative methodologies. So before we do that, these six which are valid assumptions, if there are any doubts, I'd like to clear that before we move forward to those which are seemingly invalid for many situations but continue to be used, and therefore it's also there in your textbook, the other assumptions, and therefore we will make some of those assumptions in many of the classes. But I want to give you an exposure to what is the alternative today. But before that, as I said, if there are any doubts in these first six assumptions, I'd be happy to clear that. Okay, so let's go ahead with the first of the assumptions, which is kind of dicey. One is the plane stress state. So many of you would be aware of this if you are especially from a mechanical engineering or aerospace engineering background. The strength of materials course would have exposed you to this particular assumption of the plane stress state. What the plane stress state basically means is that all these stresses are within a plane, and typically the coordinate system is chosen such that x1 and x2 are in that plane in which the stress is plane in nature, and therefore the only stresses would be along the x1 and x2 directions, namely sigma 11, sigma 22 and sigma 12, or what we call as tau 12, the shear stress in the plane. The other stresses are all equal to 0. So now let's see what could be the issues with this kind of a situation. So if you look at the laminate that you see at the right bottom end of this slide, most structures are going to be of this nature, whether it is going to be the skin of the wing, the fuselage, or the typically panels that we are talking about. There will be a small curvature because these are shells rather than plates, but what is shown over here is a plate-like structure. But even if you look at any of the one-dimensional stiffening structures like the spars, stringers, etc., you would see that they would typically be of this kind, just that the you would have the width also small compared to the length, and therefore you would have two small parameters basically associated from the geometry itself. But for that, predominantly you would have a laminated structure like this, many layers of composites lamina which are placed one over the other at different angles, the fiber making different angles to the structural directions, and for the appropriate reasons, which predominantly come from the fact that we are looking at the dominant loads which we know during the mission profile of an aircraft or any other flying vehicle, which are the directions in which the loads dominate, and therefore we would like to have as many fibers along that direction as possible. But we know that as the mission profile changes, or even in a particular phase of the mission itself, there could be multiple direction loads coming from various sources, and therefore it is essential to reinforce it in more than one direction, which is what you see in the form of a laminate. Now, in such a laminate, which is typically a thin structure, in other words, its thickness is small compared to its length and the width, in such a situation, if you have only in-plane loads, then you can get a plane stress state. But as you know, this could be a skin panel, in which case there is going to be a pressure load on top of this, and basically a pressure differential between the top and the bottom. Now, what happens in such a situation? When you have a pressure on the top and the bottom which are different from each other, obviously there is going to be a stress in the direction of the thickness, which is a normal stress in the direction of the thickness because of that pressure, and that should be a boundary condition for the structure on the top surface, and therefore if you take the top lamina, for example, there is going to be a normal stress which is perpendicular to the surface of this plane. So suppose we, as I said, introduce the x1 and x2 coordinate along the length and the width, and the x3 coordinate along the thickness of this sheet, then what we are saying is that there is a normal stress sigma 33 which should be equal to the pressure distribution on the top surface as a boundary condition there, and therefore internally also there should be a non-zero sigma 33. But what the plane stress state is saying is that the only stresses which are non-zero are the ones which is along the length, which is sigma 11, a normal stress, the one which is along the width, which is sigma 22, again a normal stress, and the in-plane shear stress, which is sigma 12 or tau 12, which is parallel to the edges of these, the four edges of this plate. Now, sigma 33 being a non-plane stress, or what we call as an out-of-plane stress, therefore is not allowed according to this particular assumption, whereas in reality that's what the flight vehicle structure actually is experiencing. But as we shall see when we move forward, the pressure distribution that is there on the top is actually causing more of a bending rather than the compression along the thickness direction, though that stress sigma 33 is non-zero, it is still negligible compared to sigma 11 and sigma 22, which are the bending stresses caused by that. Because you have a plate, you have a pressure distribution on that. Because of the pressure distribution, it is basically changing its curvature. Initially, it has a certain curvature which goes along with the airfoil cross section, and then there is a small change in that curvature which is happening, and that change in curvature is dictated by the bending stresses, and that bending stress is actually caused by this pressure distribution on the top surface, because you have a transverse stiffener which is a rib at this end, a transverse stiffener, a rib which is at the rear end, and then you have either a spar or a stringer coming at these two ends. So you have a panel which is kind of open over here on the top, and these four, that is the two spar or stringer and the transverse stiffener or the rib, act like supports for it. What you typically idealize in your strength of materials course as, let's say, a cantilever condition where you have a fixed end one end and free in the other, or a simply supported, etc. Somewhere in between the simply supported and fixed end is what you would typically have these providing. So they're not exactly that. So we need to go for more realistic boundary conditions, but for most practical purposes, to start with, for a preliminary design, let us say, it is good enough to take these as fixed ends. So in other words, you have a panel which is fixed at all the four edges, these four edges that you have, and then you have a pressure distribution as the main load that is coming over here, and that pressure is typically different from whatever is the internal pressure there, because it could be a, let's say, a fuel tank or whatever, which is may or may not directly be exposed to the skin, because you would typically have back kind of a structure within, so which may or may not be touching, but essentially what you have is a pressure differential between the top surface of the skin and the bottom surface of the skin. Now, as I said, that is causing a sigma 33, which is a normal stress out of plane and therefore violating the plane stress condition. But nonetheless, the main effect of that pressure is to basically bend this structure in this direction as well as bend it in the x2 direction. And because of this bending, you're going to have stresses which are sigma 11 over here and sigma 22 over here, which are basically exerted by these supporting structures in order to transfer that pressure load onto themselves and eventually to whatever they are connected to. So that being the situation, you would actually see that once we make certain derivations, these normal stresses sigma 11 and sigma 22, which of course vary along the thickness from tension to compression. In this kind of a scenario where you have a bending moment like this, the top surface is under compression, the bottom surface is under tension. So under such a situation, you're going to have these sigma 11 and sigma 22 values, maximum compression on the top face sheet, and the maximum tension on the bottom face sheet, whatever in the laminate you are actually having. What is actually happening is that this bending stress that is there, sigma 11 and sigma 22, which are a function of that pressure. So if the pressure were not there, they would not be existing, but the presence of that pressure brings in these bending stresses. And if you look at this laminate over here, the top surface and the bottom surface, the topmost lamina and the bottommost lamina would be undergoing maximum value of that stress, and that stress would be much more than the pressure that is coming over here. And to some extent it would depend upon how small the thickness is compared to the other geometric features like length and breadth of the laminate. So that being the case, yes, sigma I3, that is sigma 33 in this particular case, is non-zero, but it is negligible or small compared to sigma 11 and sigma 22. Therefore, plane stress seems to be a reasonably okay assumption, but it is not exactly zero, because plane stress takes it as zero, whereas the reality is that these stresses are negligible compared to whatever is actually the applied stress, which is the pressure, which is what is the order of magnitude of sigma 33. Now, in addition to that pressure, you know that as the air flows in the chord direction, you're going to have a boundary layer which is going to come up, which you probably will study as part of your other core courses, and that boundary layer will okay, thanks Vignesh. So as you see that particular boundary layer, within that there will be a viscous effect, because of which there will be a shear force which is acting as well, and that shear force per unit area will cause a shear stress. So that shear stress in turn is an out of plane shear stress, and this is an in plane shear stress. If this is the one direction, this is the two directions, so this is an in plane stress, whereas what we are talking about now is a shear which is on the top surface over here, because the normal to the top surface is the x3 direction and the direction of this is the x2 direction. So you have a tau 23 which is coming over here, which is a out of plane shear stress, what is called as a transverse shear stress, as opposed to an in plane shear stress. Now this transverse shear stress is also something which is not allowed by a plane stress state approximation, which takes that to be equal to 0. Now, once again, yes, it can be shown that this is actually kind of negligible compared to the other bending stresses. Therefore, you can take it as small, but you cannot ignore it. And what happens when you ignore it is the fact that you cannot predict delamination. Delamination is a mode of failure very common in composites, where two layers are getting separated from each other. One reason why it could happen is that there is a sigma 33, because that is going to peel away, and therefore it's called a peel stress, and therefore there's going to be a debonding between two layers which is going to occur. Now if you're going to take a plane stress state, you're going to ignore the sigma 33 completely, and therefore this peel will not be allowed. In addition, the delamination can be caused by a shear like this as well, in this direction or this direction, and that is basically your tau 13 and tau 23, and according to the plane stress state approximation, you are ignoring both of these. We have a shell or plate-like structure in which we are introducing a coordinate system. So if you want a dextral triad, which means that the cross product of a vector b1 and b2 should give you a positive b3, and therefore the direction of the x3 coordinate is downwards over here. Now what we are saying in the case of the plane stress approximation is that your sigma I3 is equal to 0. Of course, all Latin indices as before vary from 1 to 3, which means that one of the normal stresses, that is sigma 33, and two of the shear stresses, tau 23 and tau 13, are all taken to be 0. But in reality, what is happening is that they are all small compared to your sigma alpha beta, by which we mean all Greek indices vary between 1 to 2. So what we are talking about here is sigma 11, sigma 22 and tau 12, which is called as an in-plane shear stress. As opposed to these two, which are called as transverse shear stresses. Can one of you confirm if you are able to see what I am writing now?
Yes, sir, we can see.
Okay, great. Now, this difference is very, very critical. that amongst the shear stresses there are two kinds, the in plane and the transverse. Similarly, along the normal stresses also there are of two kinds, these being the in plane normal stresses and this being the out of plane normal stress, because their behaviors are going to be, of course, one set is smaller compared to the other, but other than that, in terms of the material behavior also you will see a lot of difference. So this terminology is something that you have to get used to. Okay. So whereas we are taking the approximation to say that sigma I3 equal to 0, in reality what is actually true is that it is very small compared to sigma alpha beta for most typical loading situations. So that is something that you need to keep in mind, which is why I indicated this plane stress state in a red font, that you need to be aware of this fact, because if you don't take this into account, you will not be able to predict delamination, which, as I said, is a very important mode of failure in the case of composites. In addition, even in the healthy structure, you're not able to, you're not able to predict the delamination. The second is you're unable to satisfy the boundary conditions, which include the pressure distribution on top of the wing surface or fuselage surface, etc., and the bottom as well, and of course the shear due to an inviscid flow, which involves a viscous boundary layer. Okay, so there's a question as to what kind of material I'm referring to here. So right now it doesn't matter. So I'm referring to the stresses at a particular point in a structure, irrespective of whether it is made out of a composite material or metallic material. And the isotropy, anisotropy or orthotropy do not matter over here. So many of these assumptions that I'm making are kind of independent, but we are using them in conjunction, one along with the other, in order to have additional simplifications. Is that clear? Have I answered that question? Okay. So welcome, Subhashish. So these are some of the things that are the disadvantages of making a plane stress approximation. Also, you will see that in fact you will not be able to satisfy the compatibility conditions exactly. So the compatibility equations, as you know, are the ones which are introduced predominantly to take care of the fact that you have only 3 displacement variables, and you have 6 strains which are defined in terms of the 3 displacement variables. So in other words, you cannot have 6 independent quantities, that is the strains. They are related to each other by means of 3 equations, because only 3 of them can be independent, because they're all defined in terms of the 3 displacement variables or measure numbers along x1, x2, x3, what we call as u, v and w scalar quantities, which along b1, b2, b3 becomes the total displacement vector, which we will refer to as the small u along b1, which is b1, the b system being unit vectors, v along the b2 direction and w along the b3 directions. Sometimes we might also call, instead of uvw, we might call it as u1, u2 and u3 as well, to be a little more consistent with what we have over there. Now what this plane stress approximation does, that is sigma I3 equal to 0 over here, is that it will create an error when you're trying to satisfy the compatibility equations as well. So in other words, there are all these issues that you need to be aware of. These are not the only issues, but these are the 3 main issues that can cause problems in the modeling and in the results as well. So as long as you're able to tackle those issues in some other way, some kind of a correction that you do, then it should be okay. But you should be basically aware of these issues with the plane stress approximation. Now let's see what is the advantage of doing it. Is it at all necessary to do that, is what we will see in terms of what is it that it helps us with. We have this matrix, remember, we have sigma 1 1, sigma 2 2, sigma 3 3, tau 2 3, tau 3 1 and tau 1 2. And we have said that in the case of the special orthotropy, the only non-zero terms that are going to be there are C11, C22, C33, then you have C44, C55 and C66. And this is going to in turn multiply your strain vector, which now we will change the symbol for that for in order to be able to introduce the next assumption that we are going to talk about. Instead of using epsilons, which I used to in the past, I'll be using a capital gamma. So this is pronounced as gamma. So as you might be aware of, it's another Greek letter. Gamma 2 2, gamma 3 3, 2 gamma 2 3, because the gammas are tensorial shear strains, and therefore we need to multiply those by 2 in order to get the engineering ones. 3 1 and 2 gamma 1 2. Now this is what is on the right hand side of this equation, so is multiplying that. Now in addition, you have some off diagonal terms which are non-zero, which are your C12, C13 and C23. Okay, the rest are all zeros, and this is a symmetric matrix which we saw with in the case of orthotropy. So Subhashish, now we are bringing in the material aspects. So whatever we discussed on the left hand side of the blackboard are those which are not associated with the specific material. It's just a stress state that we are talking about, irrespective of what type of material it is. Now in the case of the orthotropic material, what are the advantages that we get is what we want to see with this particular approach over here. Now we also brought in addition to orthotropy, one more assumption which was related to transverse isotropy. and whereby we reduce the number of independent elements over here. We said that C22 and C33 are equal to each other, C44 and C55 are equal to each other, C12 and C13 are equal to each other, and this C55 and C66 are the ones which are equal to each other, not C44. C44 in turn is defined in terms of C22 and C23, very similar to your shear modulus or an isotropic material being defined as E by 2 into 1 plus nu. So you have one equation over here, a second equation over here, a third equation over here, and the fourth equation over here. So you had 9 coefficients, from which 4 equations reduce the number of independent variables to 5 independent variables. So this is material constants. So this is under the combination of 3D orthotropy plus transverse isotropy, and of course all the other assumptions that we already made, which include the fact that the material is elastic, it's a linear material, strain by definition is symmetric, the absence of body moments made the stress symmetric, which is why of course we were able to write it in this 6 cross 1 form. So this 6 cross 1 form that we have over here was possible because of the fact that we have this no body moments. Otherwise you would have to deal with 9 stress components. So all of these are getting added up, these different assumptions that we made, we are combining all of them, and the fact that the strain energy density exists. So all of these have made, what the strain energy density existing led to is the fact that this matrix is symmetric. Then we brought in these 2 assumptions of the 3D orthotropy, which in the principal material coordinate system led to these zeros over here. There's no coupling between the normal stresses and the shear strains, or vice versa, and also between the shear strains themselves along with the other shear stresses in the other planes. So there's only a direct effect of the shear stresses on the corresponding shear strains. There's no coupling between them. So this is valid only in the principal material directions, as I said. That is when you have the LTT prime coordinate system that we introduced in the previous class, where TT prime constitutes your plane of transverse isotropy, which is of course orthogonal in each layer to the fiber direction. Whereas this is the longitudinal direction. So those zeros that we had in this matrix that you see over here, there's a 3 by 3 set of zeros over there, plus 3 which are the shear coupling, total of 9 zeros that we introduced. From 21 we were able to bring it down because of that, and of course you had the other off diagonal terms which are still there. That is because of the symmetry you would still have of course your C12 C13 and C23 over here, which are still non-zero. So you actually have 12 non-zero elements if you take those into account, but only 9 were independent. And then with the introduction of 3D orthotropy along with transverse isotropy, we brought it down to 5 independent material constants. But still that is in a 3D state of stress. So the state of stress is still 3D. This is all the simplification that we were able to do in the previous class itself, when we were able to showcase the fact that we have the orthotropy and the transverse isotropy simplifying the problem in the principal material directions. Now we have an additional assumption that we have made corresponding to the plane stress state, because of which we can say that the sigma I3 are equal to 0. So now if we look at which are the terms over here, those 3 stresses are in the 3rd, 4th and 5th row, what I am circling with blue over here, namely the normal stress sigma 3,3, which we call as the out of plane normal stress, and then your out of plane or transverse shear stresses tau 2,3 and tau 3,1. Now all of those are equal to 0 according to your new assumption that you have made, which is the plane stress state of approximation. Now what this actually helps us is that we no longer need to deal with the 6x6 matrix that we are talking about over here, because if you are looking at this equation, a matrix equation which relates the stress column matrix to the strain column matrix, which we call as gamma, then we are basically writing the sigma as C times gamma, where this is 6 by 1, this is 6 by 1 and this is 6 by 6. But now the fact that we have these 3 quantities going to 0, that is the sigma 3,3, tau 2,3 and tau 3,1, refer to the fact that those 3 equations, because if you look at this as a single matrix equation, or you can look at it as 6 scalar equations, where the you can think of the unknowns as the strains and the knowns as the stresses. Just from a mathematical point of view, in fact both are unknown quantities, as we shall see later on in the further development of the other equations required to solve this whole problem. But purely from this point of view, a single matrix equation over here involving this 6 by 6 matrix can be thought of as resulting in 6 scalar equations, of which now 3 of the stresses, namely the sigma I3, are known, okay, according to the plane stress approximation. To be 0. Now you can use those 3 equations corresponding to your sigma I3 equal to 0 in order to solve for these 3 corresponding shear strains, which are out of plane strains. One normal out of plane strain, which is your gamma 3,3, the 2 out of plane shear strains, which are 2 gamma 2,3 and 2 gamma 3,1. Now these 3 can be solved for in terms of the in plane strains gamma 1,1, gamma 2,2 and 2 gamma 1,2. So in other words, we expand out these 3 equations. We know that the left hand side is equal to 0. So now we use the right hand side expressions to solve for these out of plane stresses, or out of plane strains rather, gamma 3,3, 2 gamma 2 3 and 2 gamma 3 1 can therefore be expressed in terms of the in-plane strains, what we refer to as gamma alpha beta, or to expand it out, basically gamma 1 1, gamma 2 2 and 2 gamma 1 2. Okay, so the out of plane strains are no longer independent. So the out of plane strains, because of the plane stress approximation, become functions of the in plane strain. So in other words, you have only 3 independent strain components to deal with. So now that you have these expressions, that is the gamma I3 as functions of gamma alpha beta, and they're linear functions, the coefficients being some kind of a rearrangement of the C elements that you see over here, the non-zero ones which are still remaining. So in terms of that, you can solve for this. Once you solve for all of these can be substituted back into sigma is equal to C times gamma, which involve, of course, 6 by 1, 6 by 6 and 6 by 1 over here, which now can be reduced therefore into a 3 by 3 matrix, which is sigma 1 1, sigma 2 2 and your tau 1 2 or sigma 1 2. Only the in plane stresses, because the others are all 0. And now you have a matrix C, which is now going to multiply only the in plane strains gamma 1 1, gamma 2 2 and 2 gamma 1 2. Okay, now the elements that you're going to have here are going to be in general different from what you have over there, because you have used this set of equations in order to substitute and then simplify that, because you can see that in this particular equation it's only the left hand side, the stresses are equal to 0, the strains are not actually equal to 0. They are non-zero, but they are not independent, they are dependent on the other strains. So you would have substituted for these quantities, the sigma 3 3, sigma 2 3 and sigma 3 1 in terms of sigma 1 1, sigma 2 2 and gamma 1 gamma 1 1, gamma 2 2 and 2 gamma 1 2. Once you have done that, you can simplify that matrix equation to give you a 3 by 3 matrix over here, which in general can be fully populated depending upon the directions that you're dealing with. If it's a non-principal material direction, for example. Somebody had a question. Yeah.
So those will be 0, right? C13, C26.
Yeah. So in the principal material directions, I'm saying that this is a general case, let us say, in the non-principal material direction. Yeah, we'll come to that shortly. Okay. So this exercise that we are doing can be done either in the principal material direction or the non-principal material direction, but just that the starting point will be different. So if you're doing it in the principal material direction, we can take this matrix as it is, what we are talking about over here with all these zeros over here, but otherwise you would have to take a fully populated matrix, and from that fully populated matrix you can arrive at this particular non-principal material directions, what is the C matrix in the case of the plane stress as well. So we have basically combined all of the various assumptions we have made all the way up to the plane stress approximation that we have introduced just now. Is that clear?
Yes, sir.
Okay. So now let's, I think, so that kind of covers the plane stress approximation. Let's go back to the PowerPoint slide over here. Are you able to see my slide now?
Yes, sir.
Yeah. Okay. So now the plane stress state is done. Now we come to the eighth approximation, which is also kind of an invalid approximation for most situations, but works and therefore is continued to be used. What is known as the Kirchhoff-Love hypothesis or assumption, which basically states that the linear in-plane strains through the thickness. In other words, the in-plane strains are the only ones which are remaining with us, gamma 11, gamma 22 and 2 gamma 12, and now we are saying that those also the behavior we are going to assume that they are going to be linear in the thickness direction. In other words, in the x3 coordinate or the z coordinate, we are going to assume that they are going to be linear. They cannot have variations higher order than linear. So what that entails, we'll go back to the blackboard. So what we are saying now is that these gamma, alpha, beta that you have, which are the only ones which remain, namely gamma 11, gamma 22 and 2 gamma 12, the in-plane strains. Now we are saying that those in-plane strains, of course they are all functions of, in general, x1, x2 and x3 in a statics problem, and of course time also in the case of a dynamics problem. For now, let's avoid that complication. So these are three-dimensional strains. They are in-plane strains. They are all only in the 1 and 2 directions, but they are three-dimensional strains in the sense that they depend on, because they depend on all the three spatial directions. Okay, so this is critical because now we are talking about the Kirchhoff-Love hypothesis. So these are two great mathematicians and structural researchers, Kirchhoff and Love. It's named after them. And this you can think of in parallel to what you are familiar with as the Euler-Bernoulli hypothesis, or what you call as the simple engineering beam theory. Can any of you state what are the main assumptions involved in an Euler-Bernoulli hypothesis, that is the simple engineering beam theory?
So one I know that plane section remains plane.
Very good. Yeah. What else? Anybody else? There's one more important assumption that is involved in the Euler-Bernoulli hypothesis.
The deflection assumed in the transverse direction is very much less as compared to the length of the beam.
Yeah, that's true. That is actually a fallout of the assumptions. That's not made over there. In order to even derive the theory, you need to make one additional important assumption. Anybody else?
Sir, transverse shear stress is zero. Sir, there will not be shift in neutral axis.
Not necessary, because the neutral axis, because when the curvature increases, the neutral axis, which is basically a straight line, start becoming a curve as well for a straight beam bending. But there's one more important thing. It's again related to section. See, both the assumptions are related to sections, so that's a hint.
So normal planes remains
Excellent.
normal.
Excellent, very good. So basically what we are talking about is, in the case of a beam, you have whatever the boundary conditions might be. For example, we are taking a cantilever kind of a condition over here. All the assumptions are related to a cross section. So in other words, what we are saying is that we are reducing this three-dimensional structure, which is actually a beam, into a one-dimensional reference curve or a line, and in doing that, what we are doing is that we are shrinking this cross section that is there to a point. Okay, so the essential beam model, whether it is Euler-Bernoulli or later we will see Timoshenko or any other higher order beam theories, or the much more advanced mathematically rigorous ones, whatever it is, all that we are doing is either we are reducing this 3D body to 1D reference curve, or equivalently we are reducing the finite area of the cross section to a point. Okay, so these are two equivalent ways of saying the same thing. That is, we are reducing a finite cross-sectional area to a point which has zero area, or we are reducing a three-dimensional body into a one-dimensional curve or line. That is essentially what we are doing. So at each cross-section, we are reducing the finite area to an infinitesimal area or a point, and which basically means that once we do it at various cross-sections, that is eventually going to lead to many points, which when joined to each other, the loci of those points become what we call as the reference curve or reference line if it's a straight beam, right? Now, the assumptions that are required over there in the simplest beam model, there are more complicated beam models that some of you might already be aware of. So what is the main assumption that we are making over there is that the plane section remains plane. So the key word is that remains. So even so whatever it is in the undeformed configuration, as the deformation increases, so there are certain things which do not change along with the deformation, along with the loading. What are they? One is that you have a beam which is basically having many cross sections which are let's say chosen to be perpendicular to the reference curve to start with, as you see in these examples over here. So what we are saying is that once the beam deforms, those cross sections will continue to remain plane and also normal to the cross section over there. So that is basically what is the assumption over there. So essentially what we are doing is that we are dividing the 3D problem into two parts. One is the smaller part, the other is the larger part. The smaller part being the cross section, because the cross sectional dimensions are small compared to the length of the beam. In other words, let's say the cross sectional dimensions of the order of B and H, the breadth and the height are very small compared to the length of the beam, irrespective of whether it's a rectangular beam or any other arbitrary cross section, as we have shown in this particular case. We are basically saying that the cross sectional dimension, whatever characteristic length we are associating with that, that is very small compared to the characteristic length which is associated with the length of the beam, that is along the x1 direction, which is along the length of the beam, right? Now that made us to make an assumption over the smaller dimensions, which is along the x2 and x3 directions, which is the plane of the cross section. We are saying that something is not as complicated as a 3D body would generally deform. One is that if it was plane to start with, remains plane. In other words, there is no out of plane deformation. And then secondly, we are saying that the plane which originally was chosen to be at 90 degrees orthogonal or normal to the reference curve continues to remain normal or orthogonal to the reference curve. So that is basically what we are essentially saying in the case of the Euler-Bernoulli hypothesis. So just like two people were involved there, Euler and Bernoulli, in the case of the plate, two people are involved who are Kirchhoff and Love. Okay, and their assumptions are along very similar lines. Now instead of a beam, we have a plate or a shell for that matter. And we are taking x1 along this, x2 along this, and therefore for a right-handed dextral coordinate system, you should have x3 downward, right? Now, what is the equivalent of a cross-section for a beam in the case of a plate? What are we talking about as the smaller dimension over here? The smaller dimension in the case of the beam arose because of this B and H being small compared to L. Now here we are talking of the thickness T compared to the length and the breadth of the plate is small. So in other words, T is very small compared to B comma L, right? Either B or L, whatever is the characteristic length along the in-plane directions. Now, what is the equivalent of a cross-section of a beam? Here we said that the cross-section reduces to a point. What are we talking about in the case of a plate instead of the cross-section?
Line.
Very good. So now let's first introduce, instead of a reference that we are talking about here in the case of a curve or a line in the case of a beam, what is the reference that you're going to have in the case of a plate or a shell?
Reference in the sense, sir, I didn't understand.
Yeah, so here we reduce the 3D body in the case of a beam here. So you see that we started with a 3D body, which is a beam, which is also what we are doing with a plate or the shell. We are starting with a 3D and then we are reducing it to a 1D. Once we reduce it to a 3D to 1D, we no longer deal with a body, but we are dealing with a curve or a line, right? Is that clear?
Yes, sir.
Yeah. So when we are moving from 3D to 1D, we are reducing a body to a reference curve or a reference line. That could, for example, be the loci of the CG of the cross section. So at each cross section you find out the CG and you just join all the CGs of all those cross sections, and then you get that line which you can call as the reference curve or reference line. Instead of CG, you might want to choose the intersection of the neutral axis. There are neutral axes in both the x2 and parallel to both the x2 and the x3 direction. Where they meet in the cross section is basically the point at which, irrespective of which is the direction of bending, you would not have any stress, either compressive or tensile, and therefore we could call that. Or later on we will see, some of you might already be familiar with these terms, it could be the loci of the shear center of the cross section at various points, or it could just be one corner of a particular rectangular cross section that might be more convenient for you for a particular application. So any arbitrary point on the cross section is chosen, and those arbitrary points for different cross sections are all joined together and lead to this reference, which in that case of a beam is a curve or a line. So what would be the reference in the case of a plate or a shell, where we are reducing, once again we are starting with a 3D body. Now we want to reduce that to a 2D, right? There we reduced from 3D to 1D to go from a regular body to a beam, reference line or reference curve. What do we do to go from a 3D body in the case of a plate or shell to go to a 2D? What will be the reference there? Yeah? Anybody? Can you repeat that? I didn't hear it clearly. Sheet. Very good. Okay. So you're saying sheet. So more precisely, we are talking of a zero thickness sheet. What in a mathematical parlance is called as a plane in the case of a plate. Okay. And in the case of a shell, it is basically a surface. Okay. So for a plate, we go to what is known as a reference plane, and for a shell we go to what is known as a reference surface. For example, it could be the midplane of this plate. So that is an example of a reference plane. Or if it's a shell, then it could be the mid surface, which could be the example of a reference surface. But again, it's not necessary to do that. For example, the aerodynamicist might prefer to use the top surface of the plate or shell of a wing panel, let us say, as the reference surface, because he knows all the quantities over there, and therefore would like to use that as a reference surface. Doesn't matter. But all what we are doing is that this finite thickness that we had, we are reducing it to zero. So you had a finite thickness, but because that thickness T is small compared to the other dimensions of the problem, namely B and L, therefore we are having the possibility of reducing that thickness to zero thickness and dealing with the plate. Now, how do we reduce that is where our friends Kirchhoff and Love come into picture. And their assumptions are very similar to what Euler and Bernoulli said about the plane section remaining the plane and normal sections remaining normal. One is remains, the other key word is that they were talking about sections, because that is the smaller portion of this 3D problem, that is the beam. The section dimensions are small compared to the length. Now what is small here compared to the length is basically the thickness direction, that is T is small compared to B and L. So now we are, instead of talking of sections, the equivalent thing that we are talking about over here is the normal to the reference plane or surface. Okay. So the normal to the reference plane or surface, that is, if you take this plate at any given location, we are talking of this element over here, that is basically the normal. So this is whatever we are going to, we did with the reference, the cross section of a beam, reducing it to a point. Same thing, we are going to reduce this normal to a point, which is basically the point at this particular location where the normal intersects with respect to the reference plane or reference surface. That point is what we are reducing that normal line to. Here what we did is, we started, in the case of the beam, we started with a finite area and reduced it to a particular point. Here we are starting with a finite length of a line and reducing it to a particular point. So that is all, that is the difference. So if you understand engineering beam theory, which I'm sure you should from your strength of materials, you would be very easily able to understand where Kirchhoff and Love are coming from. Because now we are going to revisit these for the case of the plate or a shell. Now what Kirchhoff and Love say about the plate and the shell is once again a set of two assumptions. Here they talked about a plane section remaining plane. That's what Euler and Bernoulli did for the beam. Here we are going to now talk about normal to reference surface or plane remains straight. And unchanged in length as well. There is an inbuilt assumption that we didn't make over here, that the plane section not only remains plane, same size and shape, which we know is not true actually, because even the simplest isotropic material will have a Poisson's effect. So in other words, when you are having even a pure bending situation, you would see that the shape of the cross section would actually change because of the Poisson's effect, unless of course for a specific material the Poisson's ratio is 0, you would see that that would happen. And in the case of composites, things are much more complicated. So equivalently what we are saying is that we are taking a normal over here, and we are saying that that normal remains straight and unchanged in length, and also corresponding to what we said over here for the beam, normal section remains normal to, of course there it was to the cross section, to the reference line. Here to the reference plate, what we are saying is that to the reference surface or reference plane, we are saying that the normal to reference surface remains normal. Okay. So is this analogy clear for you, that what we are doing with the smaller dimension of the beam, which is the cross section reducing to a point, same thing we are doing for the normal line element, which is perpendicular to the reference surface and straight. We are basically saying that it remains straight, it remains of the same size, and it remains normal to the reference surface. So in other words, that plate that you had over here could undergo some kind of a deformation over here, and still anything which was normal to that plate, that line remains normal. Remains normal to this and of the same size. So if it was a height t, it remains the height t, and that time it was perpendicular to this plane and remains perpendicular to that. So that is basically what we are doing. We are saying something about the smaller dimension. The smaller dimension in the case of the beam happened to be the cross section over here, and in the smaller dimension in the case of a plate or a shell happens to be the normal line element over here. So whatever we said about the cross section over there, we are now saying about the normal line element over here, that there is a certain behavior of its deformation irrespective of how the reference surface might, as we have shown here, it's a large deformation and rotation that we have shown for the reference surface itself. Same thing in the case of the beam, we showed that it can be having very large deformations over here, and the cross-sectional rotations can be very large as well. But whatever it is doing, it is doing like a rigid body. So the key is that whether you're taking this or that, the two assumptions, we are dealing with a smaller dimension as a rigid body. So in the case of the beam, we are saying that the cross section is a rigid body, is assumed to be a rigid body. Whereas in the case of the plate or the shell, we are saying that the normal line element behaves like a rigid body. Okay, so now what is the equivalence of that? We can come back to what we were looking at over here in terms of the 3D strains. We can now say that these 3D strains are functions, yes, of x1, x2 and x3, which is why they are called as 3D strains, because they are dependent on three spatial coordinate measures, and that's why they are called as 3D variables, but can be written in terms of 2D strains, or in other words, those which depend only on the in-plane coordinates measures, which is basically your x1 and x2, not on your x3. Okay, so what Kirchhoff and Love assumed is that these in-plane strains gamma alpha beta are equal to epsilon alpha beta, which is function only of x1 and x2, not of x3, plus there is a linear dependence on x3 through the curvatures, which we will call as rho subscript alpha beta, which are also functions only of x1 and x2. In fact, there is an equivalent approximation in the Euler-Bernoulli beam theory, where we take the 3D strains to be related to only the 1D strains, what is basically the extension of a beam, the twist per unit length of the beam, and the two bending curvatures in two different directions, which are all functions only of x1, which is basically your coordinate along the reference curve or the reference line, which I have now marked in yellow. That basically, that x1 is what determines those 1D strains, and in terms of those 1D strains, all the 3D strains can be expressed. We will not go into that right now. We will go in steps. We are going from 3D to 2D, and from 2D it is possible to go to 1D. So in other words, we are doing what we referred to in one of the earliest classes of this course as the dimensional reduction, that is reducing the number of dimensions from 3, that is from a 3D body, to a 2D body, which is a plate or shell, and then further reducing that to a beam where possible. It is not possible, for example, in a cover skin panel, etc., but it is possible in the case of a spar or a stringer, where we can go ahead and make a further dimensional reduction to 1D. Now let's stick to 2D alone. So all the assumptions that we have made so far, that had led to this particular expression for the stresses in terms of the strains, where both the stresses and the strains were in terms of three-dimensional quantities. In other words, your sigmas are all functions of x1, x2 and x3, apart from the time as well in a dynamics problem. Same way the right hand side. But now we are saying that because these strains can be broken up into two parts, one is basically what we refer to as the mid-plane or mid-surface in the case of a shell, strains, which are of course epsilon 11, epsilon 22 and 2 epsilon 12, which is the in-plane shear strain. The in-plane normal strains. Similarly, you have this quantity, the rho alpha beta are again 3 in quantity. We're talking about a rho 1 1, a rho 2 2 and a 2 rho 1 2. Now this is a twisting curvature. And all of these are of the reference surface. So these are also of the reference plane or surface. Similarly, your curvatures, these two being bending curvatures, okay. Now the bending curvatures and the twisting curvature, both of the reference surface if it's a shell, or a reference plane if it's a plate. And these are all functions only of x1, x2, because the reference surface or reference plane has only two coordinate measures, namely x1 and x2, which is within that plane or within that surface, x3 being along the direction which is normal to both of these. So at this stage I'd like to pause and find if there are any questions. I'll try to answer them.
So like in the plates, x3 is a function of the other two directions, x and x2. So in the beams also, in the EB beams, orthogonal beams also, there will be some dimension which is a function of the other two. Is it like that?
Yeah, let me clarify that. See, x1, x2 and x3 are either in the case of the plate or the or the beam. All the three cases, these are independent spatial coordinates, okay. All that we are saying is that there is a order of magnitude difference between some of these coordinate measures in terms of their lengths. This is in the case of a beam, where we say that this is along the reference curve and this is along the reference cross section. So this is the case for the beam. On the other hand, for the case of the plate or shell, we are talking of both x1 and x2 being large compared to the thickness coordinate. So this is a plate, and if it has initial curvature, it is a shell. Now we are referring to this as the reference plane or surface, and this as the reference normal along the thickness direction. Now what we are saying is that we are reducing in the case of the beam, we are reducing the 3D body to a 1D body, and here we are reducing again a 3D body, but this time to a 2D body, which is their reference plane or the surface. In doing that, we are eliminating one of the dependencies. That is, in the case of the beam, we will be only talking about x1 coordinate. We will not be talking about the x2 and x3 coordinate, which are shrunk to a point. Same way here, we are shrinking the x3 coordinate to a point on the reference surface, and therefore we will be only talking about x1 and x2, which are remaining. But nonetheless, the actual body in both the cases, whether it is a beam or the shell, is actually a 3D body, and we'll have to revisit every point over there and do what is known as a recovery. which is going back after the 2D analysis is complete. We want to go back to the 3D body and look at each point what has actually happened in terms of what is the value of the stress, what is the value of the strain, what is the value of the displacements that are there. All of these tensorial quantities will have to be determined at all the locations x1, x2 and x3, and if it's a dynamics problem, with respect to the time as well. The same thing was done in the case of the beam as well. All of the analysis is done with the 1D problem, but then eventually there also we'll have to do what is known as a recovery. Only then it would be possible to predict failures, for example, or to redesign and make the structure better design, to change the cross-sectional shape or cross-sectional size, various parameters, the material distribution within it, if it's a hybrid kind of a cross-section, which materials go. In the case of a plate or shell, how many layers you want, each layer, what is the angle of the fibers that you want, etc. All of these decisions can be possible only when you do this recovery, that is going back after you finish the 2D analysis, which is much easier than doing a full 3D analysis. You do a 2D analysis and then come back and recover all of the 3-dimensional fields, which are your stresses, strains and displacements, all being functions of all the 3 spatial coordinates apart from time. So whatever we are reducing from 3D to 2D, we have to recover once the analysis is complete, whether it's a beam or a plate. Have I answered your question?
Yes, sir. Understood, sir. Thank you.
Okay. Anybody else? Any questions?
Hello, sir.
Yes.
Sir, I have one doubt that the moment we make these assumptions that the plane section remains plane and normal remains normal, we are also, as a consequence of these two assumptions, we are actually what we get that this angle between these lines along x-axis and one axis and the line about this along this 3 and 2, these angles do not change, right?
That's correct. Exactly. So because we are saying that the normal remains normal, basically the 90 degree remains 90 degrees. So we are not allowing for any rotation in the case of a beam. So let me draw that. So in the case of a beam, what we are saying is that whatever the the deflection that might be there, now you had your original reference line or curve over there, and you have your deformed reference line or curve over here. So we are saying that initially whatever remained normal is basically remaining normal over here. So in other words, what we are saying is that there is no independent degree of freedom for the cross section to rotate. DOF, short form for degree of freedom. So in other words, once the reference curve is determined, the amount by which the cross section rotates is also determined. So there is no two independent quantities over there. That's where you see a difference between the Euler-Bernoulli beam theory and what is known as a Timoshenko beam theory, where now this cross-sectional rotation is independent of the rotation of the reference curve. So in other words, the reference curve, whatever the deflection, in addition, the cross-section also undergoes an additional deformation that is there. I'm sorry you cannot see my video, but later on you can check out the YouTube video, because I'm also explaining with my hands what is actually happening. So basically you have a reference curve, and you have to that reference curve a cross section which is perpendicular. In the case of the Euler-Bernoulli beam theory, as the reference curve deforms, the reference cross section also deforms along with that, rotates along with that. In other words, it is not changing its shape and size, but the amount of rotation of the reference cross section is the same as that particular, at that particular point, whatever is the change in the angle that the reference curve has made, the same is the case for the cross section as well. In other words, the cross section rotates as a rigid body, but the amount of rotation is dictated by the behavior of the reference curve, how it is deforming. On the other hand, in the case of the Timoshenko beam theory, one, yes, it is rotating along with the reference curve, but in addition it can have its own independent rotation, because of which the cross section no longer remains perpendicular to the reference curve, and that change in angle becomes an independent degree of freedom that you deal with in the case of a Timoshenko beam theory. Have I answered your question?
Yes, sir. I got my point.
Yeah, very good.
Sir,
Yeah.
one more thing
Yes.
here only.
Yeah,
So we are actually neglecting this two shear strains, right?
Exactly.
Two shear strains are zero.
very good. Yeah, yeah.
Okay.
Yeah.
I had one more doubt. I'm just lost.
So for the benefit of others who may not understand what you just mentioned, what he is referring to here over here is the fact that we are ignoring the gamma 1 alpha, which means engineering you put a 2, so that is basically your 2 gamma 1 2 and 2 gamma 1 3 are the additional rotations of the cross section. So you have a reference curve, then you have according to Euler-Bernoulli beam theory, the cross section is going by the same amount of rotation as the reference curve, but so this is Euler-Bernoulli beam theory. On the other hand, in a Timoshenko beam theory, you can have an additional rotation that is there, which is given by this particular angle, and in a plane, if you see perpendicular to this, you would have a rotation along that as well, which is what 2 gamma 1 3 is. So what Timoshenko beam theory is saying that these are not equal to 0, whereas the Euler-Bernoulli beam theory is taking them to be 0. In other words, the cross section is rotating along with the reference curve. The same thing in the case of the Euler, in going from what we had as the Kirchhoff-Lau plate or shell theory to what is known as the Reisner-Mindlin plate or shell theory, where we are allowing for these additional rotations to take place of the normal. So in other words, you have that normal to the cross section. After deformation, it need not be normal. That line can undergo an additional rotation, and that additional rotation in two different directions is what we refer to as the transverse shear strains over there. So we are basically allowing for those two additional degrees of freedom in the Reisner-Mindlin plate theory, which is equivalent to your Timoshenko beam theory, as opposed to the Kirchhoff-Lau, which is analogous to your Euler-Bernoulli beam theory. So the whole idea here is not to bog you down with the mathematics, but to give you the bigger picture of how 3D bodies, in reality everything is a 3D body, but how those 3D bodies are getting reduced in a mathematical sense to either a 2D reference surface or plane in one case, or the reference curve in the, or line in the other case. Okay, is this clear? So the plane is synonymous with line, the surface is synonymous with a curve, and these are essentially for two different kinds of structures that we are dealing with to start with. That is, one where you have the cross-sectional dimensions small compared to the length, the other where the thickness is small compared to the in-plane dimensions. So these are for two entirely different kinds of structures that we are dealing with. One is the plate or shell, the other is the beam, or what you can call as a rod or a column or a shaft, or elements of a truss or a frame. So essentially I'm giving you a bigger picture of a canvas on which you can consider all of these from the same kind of mathematical paradigm in terms of what assumptions are required and where it leads to. The overall idea is that there is a dimensional reduction, in this case from 3D to 2D, and in this case from 3D to 1D, so that it simplifies our life. But as I said, you should always come back to understand what is the 3D, which is through what we call as the recovery. So I just took advantage of your question to explain a few more things to finish up the bigger picture, but I'll let you ask the other question that you wanted to.
Yes, sir. Sir, my another question is, here we are in case of beam, we have two geometric parameters which are quite small. That's why we have been able to reduce the dimension from 3D to 1D. And in case of plate, we had one small parameter, that is the thickness. So we went from 3D to 2D.
Correct.
Sir, can we do this thing for a general? I mean, if we go to some abstract problem where we are dealing with some in-dimensional situation, say hypersurface.
Right.
Can we extend this theory there also?
Yeah.
Can we?
I'm so very glad that you asked this, because it requires a lot of thinking to ask this question. Absolutely yes. And in fact, there's a whole body of research that goes on into reducing any n-dimensional space to a m-dimensional space where m is smaller compared to n. And this m and n dimensions need not be all spatial dimensions. There can be certain physical dimensions associated with certain physical variables, etc. And so in other words, for example, associated with the physics of the problem. While introducing the various types of structures, I talked to you about, for example, a sandwich kind of a construction where you have a face sheet, for example, and then a core, which could be a honeycomb or it could be a foam, and then one more face sheet that is there over here. Okay, so now this problem would depend upon, for example, the ratio of the material properties. Let's say to take this simple example, let's say you have just a metal over here and foam and a metal over here, and so let's say E of the foam and Young's modulus of the metal. Now E of the foam is very small compared to EM. Now just like you had a small parameter over here with H being small compared to B and L, and therefore using H by B and H by L as the small parameters in order to enable this dimensional reduction from 3D to 2D. Similarly, I can use the ratio of EF divided by EM. I'm getting confused with the fiber and the matrix. Here I am actually referring to as foam and metal, because otherwise it will be the other way around. Now this is a small parameter compared to unity. Now I can use this as a way to do a dimensional reduction in an abstract sense, like what you're talking about, where we can actually reduce the complexity of the problem, whereas in the spatial sense we might still be doing the same thing like what we are doing with any other plate or shell. We are actually reducing the complexity of the problem by taking advantage of other small parameters which are existing in the system. So the whole idea here is to identify the small parameters not only from the geometry which is what we did for the beam and the shell, but also from the physics of the problem, which is what we did in the case of the sandwich construction over here, where we took advantage of the fact that this could be a small parameter, and if we take that into appropriate account in the whole analysis, we can use that to bring in an abstract dimensional reduction in the overall problem. Does that answer your question?
Yes, sir. Thank you very much.
Yeah. Anybody else? Any questions? Okay, then. Thank you very much. We will meet on Thursday, continue with this, bring in more mathematical perspectives into the bigger picture that we already introduced so far. Thank you.
Thank you, sir.
Welcome.
मृत्युंजय मंत्राः
त्र्यंबकं यजामहे सुगंधिं पुष्टिवर्धनम् उर्वारुकमिव बन्धनान् मृत्योर्मुक्षीयमामृतात् एते सहस्रमयुतं पाशा मृत्योर्मर्त्याय हन्तवे तान् यज्ञस्य मायया सर्वान् वयजामहे मृत्यवे स्वाहा